Okay, welcome back. We're going to be getting started in a little bit. So let's go ahead and take a look at this circuit that we have right here in front of us. Now, this circuit, I have to be very critical just because there's a lot going on at this point in time. So right here, we realize that we have some independent voltage source. We have a current that's predefined for us called IB. We have this independent voltage source, this resistor, this current dependent current source, which has a defined voltage called VC, and this dependent voltage source. So when we're going to solve this, we have to be extremely careful about how we label our polarities. Now, again, I want to reiterate that it is your choice to put in whatever polarities you want. It's just that once you pick that polarity, you are stuck with it, and you have to carry your calculations through with it. So let's go ahead and assign our polarities, our voltages, our currents in all the directions that we need to. All right, so I'm going to choose red as our voltages. So let's go ahead and call this voltage right here voltage of source 2. This voltage I'm going to call in the direction of a voltage drop, which is IB. I want this to be called V10. Now again, keep in mind that these voltages and polarities are arbitrary. I want to keep reiterating that because if you choose to put this as a negative right here and a positive right here, that will work. It's just that when you write your Ohm's law, your power, you have to be careful that you are not putting in a positive value. So for example, if I were to evaluate power here, it would be negative V times I, mainly because my current is traveling in the direction of a voltage rise. So in obeying passive sign convention, I'm going to have to follow that way. So to continue, I'm going to choose mine to be in the direction of a voltage drop. That way I can use the positive version of passive sign convention. Now, right here, I'm going to stick with the polarity that's defined in the problem. Let's go ahead and call this voltage of source 3. I'm now going to come down to this 200 ohm resistor. I'm going to label this voltage as V200. I'm going to call this voltage right here V500. And now I have to be critical thinker when I'm looking at this. So I see that there's some current called 29 I beta or IB entering. Now, how do I want to define this polarity? I want to define it in such a way that it goes in the direction of a voltage drop. Now, the only way I can make that happen is if I have a positive terminal right here and a negative. Now, again, if I wanted to switch it, I can. That's fine. And put a positive negative here. It's just that I must obey passive sign convention and compensate for that. So, my choice, I'm going to put a positive right here and a negative right here. Now, as far as labeling the source, I'm going to have my positive terminal right here, my negative terminal right here. I'm going to go ahead and call this VC, just as it is labeled in black. Now, the voltage of this source is 25 volts. I want to keep the polarity the exact same and keep it as 25 volts. So, I have labeled all my voltages. That's done. Now, let's label our currents. So, I want the currents to be purple. So, when I'm doing my currents, again, being critical, I have to think to myself, does this violate KCL? Does this violate KVL? In the case of this IB right here, or I beta, I see that I beta is going to travel through this element, and therefore I can call the current traveling through this element, labeled in purple, also IB. Now, when I'm labeling this current right here, I see that a current called 29 IB is entering this resistor. So I'm going to keep that consistent and say that, hey, this current travels all the way through here, enters that resistor. That's also going to be 29 IB. So when I'm doing this, I have my 29 IB traveling through there. Now I'm going to do another current. This current is going to come down here. It's going to go in the direction of a voltage drop, and I'm going to call it I200. Now you can choose whatever naming scheme you want. Anything works as long as it's consistent with you and you understand why you labeled it. I like to do mine after the resistor value. Okay, now looking at this element here. This one's kind of tricky because when we're looking at it, I'm only analyzing this. I can say for sure that because these elements are in series, they're going to have the same current. Now, from KCL, if I'm looking at this node right here, I have to realize that the current leaving this node is 29 I beta. Now, to make that a valid statement, looking back to our valid interconnections, we see that the current leaving this must have also been equal in magnitude to that 29 I beta. So I want current to flow in this direction right here, right? Let's not do anything fancy yet. We're going to want current to flow in this direction. So the only way to make that happen is that this current will be called 29 I beta. It's the same current that flows because all of these elements are in series. So let's do that as 29 I beta. Alrighty. So we have one more to label. Same exact story on this side. I see that, hey, I'm at this node right here. Well, what current could be leaving that node? What enters must be equal in magnitude to that that's leaving. Therefore, the only way to make that satisfied is that this current right here is exactly I beta. All right, so let's just check. We have this current labeled. This current has been labeled for us. This current's labeled. This current's labeled. This current's labeled. This current is labeled for us, and this current is labeled for us. So let's go ahead and check that off on our to-do list. Now, the next step I want you all to practice, and I'm going slow right now, of course, so if I'm kind of boring, speed up the video, no worries. But the idea is that you can plan out your circuit analysis in such a way that it makes it easy for you. Instead of doing random tricks and random motions, you want to be able to have a plan, follow through on that plan, and think ahead. So let's go ahead and do plan circuit analysis. So what is our plan? In doing this, I see that I have I have this current, which is called I beta, and this is the current that flows for these two elements. Now, these three elements. I have the current 29 I beta that flows for these elements, and then I have some current arbitrary that I've labeled I200. So this I200 current would be something that I want to solve for. So my plan of attack is that I'm going to do a KVL in this loop. By doing KVL, I gather information about IB and its voltages. Once I do my KVL here, I want to plan to do a KCL right here. Why? Because I have something in terms of IB, I have something in terms of the thing I want to solve for, and I have, again, something in terms of IB. Actually, I lied. This one would be going this way, and this one would be going this way, and this one would be going this way. But either ways, I want to do my KVL, then my KCL, so that way I can get my I200 out of the common IB. All right, so we have our plan. We can go ahead and write it. So we're going to write KVL. Oops, can't spell today. KVL at our left loop. Then KCL, I'm going to call this node A, and I'm going to highlight it for us. All right, we're going to do a KCL at A. So let's go ahead and do this. So when doing our KVL, I'm going to start at what I call V10. I'm choosing to do my KVL in this motion. All right, I'm going to be consistent with that in all of my videos. It's just my preference. However, you can do it you can do it in this way. That's up to you. As long as you're obeying passive sign convention and counting your polarity correctly. But like I said, I want to do this way, so I'm going to. So in doing this, I say that I have, let's actually write our steps. So KVL at left loop. KVL in the left loop will give me my minus 15.2 volts plus my V is equal to my R times I. So I'm going to have my R as 10 kilo ohm times, what's the current? I beta, or I beta, minus my 0.8 volts. And I'm hitting this terminal right here. I'm hitting what I labeled as positive. So plus 200 times I 200. And that's all going to be equal to 0. All right, now what I'm going to do is my KCL. So like I said before, my KCL is going to read just as so. I have I beta is the current that is entering this node. I have I 200 leaving. And I have a 29 I beta entering. So obeying our passive sign convention, I'm going to say that I have minus I beta plus my I 200 minus my 29 I beta equals to 0. So as we can see, my value for my IB will equal to I 200 over 30. All right, so now my plan of attack. I've done my KCL and I've done my KVL. What I want to do now is plug in this IB into here. What this allows me to do is have one equation and one unknown. Because I'm getting it in terms of I200, I can then solve for I200. Likewise, I then solve for IB. So let's go ahead and do that. When solving, so we're going to say that known or knowing that IB equals to I200 over 30, we're going to have the equation that reads minus 15.2 plus 10k times I200 over 30 minus 0.8 plus 200 times I200 equals to 0. So in doing this, I can then solve for I200. All right, so my I200 from this will equal to 30 milliamp. Likewise, I just said that IB, or I beta, whichever you want, is going to be equal to my I200 over my 30. Therefore, I have 30 milliamp divided by 30, which equals to 1 milliamp. All right, so we've now solved for I200, which is this fellow right here, and IB, which is this current, and also I've unlocked this current. It's just 29 times IB. All right, so let's go ahead and write this for our reference. I'm going to say that I200 equals to my 30 milliamp, and my IB will equal to 1 milliamp. Alrighty, so let's go ahead and find the voltages. When finding the voltage for my 10 ohm, that's what I'm choosing to start off on. We can go ahead and begin by writing Ohm's law. So we're going to say that my voltage of the 10 volt will equal to my 10 kilo ohm multiplied by IB, which will equal to 10 volts. My V200 will equal to my 200 multiplied by my I200. Now, knowing that I200 was 30 milliamp, I'm going to get 6 volts. My V500 will equal to my 500 ohm multiplied. Now, actually, I want to take a little bit of time to explain what I'm doing here. So, I'm doing my Ohm's law still. However, I realize that the current that's being sent through here is multiplied by some factor called 29. We're having 29 times IB. Therefore, the current that travels through here is 29 times whatever IB is. It's as simple as that. There's no need to overcomplicate it, okay? So I'm going to be doing 29 multiplied by IB. IB is 1 milliamp. Therefore, the value for V500 will equal to 14.5 volts. Now, to find VC, let's do a little bit of thinking. Right now, I don't have the tools that I need to be able to directly solve for VC. However, I do have KVL and I have KCL. So, using those two, I'm able to solve it by doing one KVL in this loop. When I do my KVL in this loop, I'm looking for my VC. All right? So, my VC is going to be my minus V500 minus my VC plus 25 minus V200. That's all going to equal to 0. Subbing it in and swapping the 0, I'm going to have 0 equals to minus 14.5 minus VC plus 25 minus 6, and my VC will equal to 4.5 volts. All right, so let's go ahead and move on to the power section. So actually, let's do a quick recap. So again, I did my KVL in this loop. The reason I'm doing that is because I realized that, hey, I have one singular current, IB. Then, by using that one singular current for these three, I also link in I200, which is unknown. In this side, I have IB, which is dependent on one of these currents right here, IB. So right away, I know that I can link these two by a simple KVL and a KCL. All right? Now, moving into power, I'm going to say that my power through what I am calling VS2, let's see, I might get rid of some stuff over here. Yeah, let's go ahead and do it right here. So my power, my VS2, again, obeying passive sign convention, let's go ahead and locate VS2. VS2, in the direction that I chose for current, is going in the direction of a voltage rise. Therefore, I'm going to have to use negative passive sign convention. So when I'm writing this, again, I stick my negative here. Let's go ahead and write the formula first, then numbers. All right. So we have our VS2, which is going to be minus, this should be P. Power of VS2. Sweet. So we have negative VS2 times IB. All right. Then we're going to have our power to the 10 kilo ohm resistor. That's going to be obeying positive, the positive version of passive sign convention. Therefore, I'm going to have V10 times IB. Then I'm going to have power through my voltage source 3. My power through the voltage source 3 will be a negative VI. Therefore, I'm going to have negative VS3 times IB, which is the proper way to label it for that one. My P200, and I'm running out of room, P200 will equal to V200 multiplied by I200. My P500 will equal to V500 times my I. So in this case, I have to be really careful because, again, we run into that goofy 29 in front of it. So because it's goofy, we still are going to include it, all right? We're going to have our 29 I beta be the current that flows to this resistor. So we're going to have the 500, we're going to have V500 multiplied by 29 times IB. My power through my source, my current source, is going to be VC times my 29 I beta. And again, why is it positive? Well, it's obeying passive sign convention. It's going in the direction of a positive towards a negative. Next, my voltage source 1. My voltage source 1 will be my VS1, my negative VS1, because of my passive sign convention. And my passive sign convention, and my 29 times IB. All right, so I'm going to go ahead and give you the solutions for the values, and we are going to verify in this space down here that our power checks out to be 0. All right. Again, all we're doing is plugging in the voltage values and the current values. The main idea behind this example is that you can understand your passive sign convention and be able to navigate the circuit with your choices that you've made. Let's go ahead and get those values going. So this power for the VS2, that's going to be negative 15.2 milliwatt. My power to the 10 kilo ohm resistor will equal to 10 milliwatt. My power through the voltage source 3 is going to be equal to negative 0.8 milliwatt. My power through the 200 ohm resistor will equal to 180 milliwatt. My power through the 500 is going to equal 420.5 milliwatt. My power through the source is going to equal to 130.5 watt. And my VS1 is going to equal to negative 725 watts. All right, and let's go ahead and do that power balance down below. I'm sorry, these should be in the order of milliwatt for the last two. Should be 130.5 milliwatt. And here, milliwatt as well. My apologies. All right, let's go ahead and do this summation and make sure that we're getting values that make sense. So we have the sum of all the power should equal to 0. All right, let's see if that's true. We have 10 plus 180 plus 420.5 minus 15.2 minus 725 minus 0.8 plus 130.5. And checking that does in fact equal to 0 watts. So this is a good way to be able to make sure that you have what you need and you're solving all the voltages and currents correctly in order to get that sum of 0. All right, and just as a recap over everything, I know it's a lot to take in on one page, but we started by labeling our voltages with some polarity that we chose. Now, as a challenge for you guys, I want you to reverse all the polarities that I did and see if you come up with the same solutions. The same circuit analysis techniques apply, the same method that I chose to use still applies. It's just that you are obeying passive sign convention in a different way. And you just have to keep track of it. It's tedious, but as long as you keep your numbers in check, you will get the right answer. So we've labeled our voltages, we've labeled all our currents, and mind you, I put the currents, when I could, in the direction of a voltage drop. I want to discuss like a special case right here, for example. Because my predefined, anything in black is predefined for me. Because the voltage is here, in order for me to not make my circuit analysis the negative of when I'm talking about this voltage, I want to put my polarity here as the exact same as this source. Therefore, when I have IB traveling through it, I'm going to have to use my negative like we did in our example. And as you saw, it checks out to 0. So we did that. We checked all our currents, and we did a plan for our circuit analysis. Now, just like I said before, I was able to visualize, hey, we're doing a KVL here. Then we're going to do a KCL because I see what values we're using. I see the variables that we have, and I know that there's 2 common variables right here. I know that this is the outlier that we were after. Once I have all the currents, by Ohm's law, I can get my voltages. If I cannot do that, then like we did here for this element, we ended up doing a KVL, right? I wanted a voltage, so I do a KVL. I want a current, for example, I'm going to do a KCL. So, having that said, I hope you enjoyed this example. Please reach out to your professor for any questions or any suggestions on what you guys want to see in the videos. Thank you so much.